Yes. I'm recording.
Thank you. All right. So now we consider a more general fractional order differential equation with constant coefficient and zero initial condition. So zero initial condition means my y of 0 is 0. So you have this fractional differential equation in this form. So again, what do? You apply the Laplace transform to both sides. So most times when you have this zero initial condition means the y of 0 is 0. So of course, immediately you should know that you're using the Laplace transform of the capital fractional derivative. If it is not stated. If it is stated capital, then you go ahead and use capital. But if it is not stated, then you know it is the capital fractional derivative. But in many cases, of course, you are the one formulating the problem. So you define what fractional derivative you are using. So for zero initial condition to exist means I'm dealing with capital. Because it is only in capital derivative that you have this zero initial condition defined. So again, when you apply the Laplace transform to both sides of 3.5. So again, this is an example you consider at home and work it out. Take the Laplace transform of the capital fractional derivative. Remember, this first one is to be s to the power of alpha minus 1, s to the power of alpha, Laplace transform of y minus s to the power of alpha minus 1, y of 0. Remember, y of 0 is 0, so it will go now plus omega square transform of this, now plus Laplace transform of this. So when you rearrange, your y of t will become Laplace inverse of this. So again, the Laplace inverse of product is nothing but the convolution of the two functions. So your g is nothing but the Laplace inverse of this first expression, which you can find. So again, you can see I'm solving this fractional differential equation, and I come to a stage whereby I have this expression 1 over .
Okay.
We can't hear you again, no.
Okay, Andrew. Dr. Andrew, can we?
He's not online again.
Let me check. I think he will soon join us. Let's just exercise some patience. I think he will soon join us. Okay, Dr. Andrew, I think you can proceed now. Hello, Dr. Andrew. I think you can proceed. We can hear you.
Yeah, I'm so sorry about that. I'm so sorry about that.
Okay, you're welcome.
There was a change of Wi-Fi from one Wi-Fi to another one. So sorry about that.
Okay.
All right. So basically, if you take the inverse of the Laplace inverse, you just get the standard expression. So this makes life easier. So you can see this is one of the applications of the Mittag Laplace. So knowing the Laplace transform of the Mittag expressions involving the Mittag Laplace function is very important. So if you don't know the Mittag Laplace function or have idea of the Laplace transform, then if you see an expression like this, you say, oh, there is no formula for this. You just run away and leave it. So but you can see the Laplace inverse will give you this final form. So by the time I take this and I plug it in there, replacing t with t minus 4, then I get the final solution for my y of t. So again, if you want to plot graphs for some of these, there are codes in MATLAB for even the Mittag Laplace function. I have some codes on this. I can also give you if you need. So again, look at this fractional diffusion problem. Again, this is a problem which is very common in physics, in engineering, even mathematics. So look at this problem we have. So you have this form, this diffusion problem. So if alpha is 1, you have the normal diffusion equation, which you know. So but now we are making it fractional. So and the boundary and initial conditions are given by this. So ux tends to 0 as x tends to infinity. And the time fractional derivative of uxt at time t is equal to 0 is f of x. So for this fractional derivative, where the fractional derivative is given at the initial point, so the fractional derivative to use will be the Riemann-Levy fractional derivative, because in the Laplace transform of the Riemann-Levy fractional derivative, the time fractional derivative of that function is defined at the initial point t is equal to 0. So here, if I see this kind of problem and I want to solve, I don't need to use the capital derivative, because the capital derivative, this will not be defined. It's only Riemann that this will be defined. So you can see. So, but now, because of this expression on the right-hand side, this double derivative on the right-hand side, again, there will be application of two transforms. So I'm going to use both Fourier and then Laplace. So if I apply Laplace transform to this expression, so I get equation 3.8. So now, for this problem, we are going to apply double transform. You can actually use the Laplace transform first, then you now use the Fourier transform. Or you use the Fourier transform, then you apply the Laplace transform. So but now I'm applying the Fourier transform. So if I apply Fourier transform, remember the definition I gave at the beginning, the Fourier transform of derivative, fractional of derivative. So when the derivative is 2, so you just have I omega in brackets squared. So that omega is like my k. So in this case, I'm using k. K is the transform function. So ik all squared. So I have it this expression. Remember when you square your I will be minus. So you're having this minus k squared and Laplace transform of k. So this kappa is what you are having here. So you have this expression when you apply the Laplace transform, the Fourier transform, sorry, to this derivative. So this fractional derivative will still be there. So it's only the variable that will now change. Instead of ukt, so you now be having instead of urt. So I'm taking the Fourier transform in x with respect to x. So my variable will change from x to k. So that's why I'm having this k here instead of x. So when you transform it, there's a change of variable. So what transform does is to change from one variable to another, but still preserving the solution properties. So remember, you apply this initial condition, which is given to you in the problem. So then you now remember the Fourier transform is given by this expression. This is the definition of Fourier transform. Now, I will apply Laplace transform of the Riemann-Levy fractional derivative, the expression in 3.8. So if I apply the Laplace transform of the Riemann-Levy fractional derivative, I'll get the expression given in 3.10, which is this one. So at this point, when you have applied Fourier transform, you have applied Laplace transform, what is the next thing? You now apply the inverse. You now apply the inverse Laplace transform. But in the order of inverse, when you are taking double transform, Laplace and Fourier or Laplace and any other transform, always in the inverse start with the inverse of Laplace. It makes the work easy for you. So if I take the inverse Laplace transform of this expression, which is given in 2.12, then again I'll have this form. Remember, again, I don't need to repeat. So we are applying the Mittag Laplace function here. So I'm taking Laplace transform in S, inverse in S, sorry. So therefore I'm considering this expression. So the inverse will just give me this form. So now, how do I get my final solution? I will again apply the inverse Fourier transform. The inverse Fourier transform of this expression will now give me the final form of the solution, which is given by 3.11. So you can see how both Laplace and Fourier transform have helped us to get the solution to our problem. So again, if you put alpha is equal to 1, If you put alpha is equal to 1 in this problem, you have nothing but you just recover the solution of the diffusion equation, the non-fractional diffusion equation when alpha is 1. So one good example of exercise you can do is you can pick the solution, the fractional solution, which is this one. You can generate the graph of this. Now make your alpha to be 1 and also generate the graph for alpha is equal to 1 and compare them. Or you can take this solution for the fractional case, solve your diffusion equation using any known method. Any known method you have, method of characteristic, separation of variable, any method you use it, solve it. Now compare your solution graphically with the solution you get from your fractional case and compare them. So this is a very good homework to do. Now look at the non-homogeneous fractional wave equation given by 2.12. Look at it. Remember the standard wave equation, alpha is 2. So now the initial conditions are given by this. Look at the initial and the initial conditions we have. So at time t we have the now time fractional derivative is given by this. So again, we don't need anybody to tell us. We are going to use the Caputo fractional derivative. Why? Because in the Laplace transform of the Caputo fractional derivative, I have initial points. At time t is equal to 0, my function value is known. So my u at time t is equal to 0 is given. Again, my time, the derivative, the time derivative of my u at time t is equal to 0 is also given. So the best form of the Laplace transform is the Laplace transform of the Caputo derivative, which we have already defined in the preliminaries. So if you apply it and simplify, so this again will be another good homework which you can give to yourself. Apply the Laplace transform of the Caputo fractional derivative. When you apply the Laplace transform, plug in this initial condition. Remember, don't forget, these are initial conditions and they are to be used. Use them. When you use them, now when you apply the Laplace transform of the Caputo, and now apply Fourier transform again. Why are you applying Fourier transform? You are applying Fourier transform in X because of this expression. You are applying Laplace transform in T because of this expression. So that's why the double transform is important. So you have this expression. So when you now take the inverse, remember in the order of inverse, I take inverse of Laplace. So I take inverse of this expression, inverse of this expression, and inverse of this expression. So one by one, this one now s to the power of alpha minus 1. So this is similar to one of the expressions we have. This first one is similar to one of the expressions we have for the Laplace inverse of the Mitac-Leffler function, which we have discussed. Remember, I said you won't appreciate those Mitac-Leffler functions if you start solving the problem. So you can go back, if you don't know what happened here, you can go back to the Mitac-Leffler function and see which one has a form close to this or closer to this. Then without even worrying yourself, it is this one. So I'll now put it here. And for this other one, look at it here. Now for this, which other one again? So for this last one, look at the form here. So again, you apply the inverse Fourier transform. What is the inverse Fourier transform? You see why it is easy for you to take your Laplace test. The inverse Fourier is nothing but your function, whatever you have. Like if I'm taking the inverse Fourier transform of this first expression, I'll just have 1 over square root of 2 pi minus infinity to infinity, negative infinity to infinity. I'll write the whole expression as it is. Look at it. I will just multiply with this. So this is why it is good to take your Fourier transform, your Laplace transform inverse first. So whatever you get, in taking the inverse of the Fourier, it's not a big work. You just write your expression, put under integral sign, and multiply with this. So same thing I do to the remaining expression. I hope we are following.
Yes, go ahead. Yeah, we are following.
Excellent. So now there is another transform again which can apply. So which is the finite Fourier sine and finite Fourier cosine transform. Consider this heat conduction problem in the finite domain with the Dirichlet data. Dirichlet data means this form of boundary and initial conditions are given at time t is equal to 0. You have this form. So no derivative. So that's one thing with Dirichlet data. No derivative. So you have this expression given. So and when there is no derivative in your initial and boundary condition, the best form of finite Fourier expression to use the finite Fourier sine transform. Because if you check the properties of the finite Fourier transform, which we have discussed earlier on, you will see that there is no derivative in the expression for the finite Fourier sine transform for the second derivative. In the initial condition, I mean, there is no derivative. So if you apply the finite Fourier sine transform to this, then you just have this expression. So again, you apply the initial and boundary condition which you are given. So you just have this form given by 3.20. So and the solution of 3.18 to 3.20 is going to be given by this. So this is nothing but an ODE. So you can see what this transformation does is to transform your problem from partial differential equation into an ODE. So if you have again an ODE, so it transforms it into an algebraic expression which can easily solve. So when you have a PDE, it transforms into ODE, which can easily solve. So you can have the expression given by 3.21. Then again, the inverse finite Fourier sine transform. Remember, the inverse finite Fourier sine transform is in terms of series. So again, look at our solution in 3.22. So for a particular scenario, when your f of x is a constant, then you have the form of solution given by 3.23. So these are things you can easily verify. And with all the knowledge you have, you can verify them. Now, for this same problem, which you have solved using finite Fourier sine transform, what if we change the boundary and initial condition? So if we now add derivative term to the boundary condition, such as this, then the finite Fourier transform can no longer help us. So the finite Fourier cosine will be the best form to use. So if you apply the finite Fourier cosine transform, the expressions are there in the introductory part of this presentation. So you can easily apply it and now get this form. So again, that will be this to an ODE, which again you can solve. So this is the first order linear ODE in T. So when you solve it, you have the expression given by 2.26. So again, you can apply the inverse finite Fourier cosine transform. Again, this is in series. So you have the form given by 3.27. Now, this should be the last thing now. I'll soon round up. Sorry. I know some of us will die, but I pray you are following. It's very interesting anyway. So find the solution of the symmetric heat conduction problem. So this is a very simple case. We have this boundary condition given. So now, look at this expression given here. So the finite Hankel transform, there is a standard result for the inverse, the finite Hankel transform of this. There is an expression for the finite Hankel transform of this. So if you take the finite Hankel transform, the definition of the finite Hankel transform, if you apply it to this, then you just get the expression from here, 3.31. And the initial condition also, you apply transform to it. You have the second expression given here. The definition of it, I've already given it at the beginning. The Hankel transform. There's a Hankel transform, zeroth order finite Hankel transform for this. The expression will give you this form, you have in 3.31. So the solution of the first order system, the expression we have in the previous bit is nothing but the first order ordinary differential equation which can solve. So if you solve it, then you have this expression given in 3.32. Then the inverse transform, Hankel transform now. Again, the inverse finite Hankel transform is in series form. So you have the expression given in 3.33. So for particular scenario when it is a constant, so you have this expression given in 2.34. So this is for a non-fractional case. Then there was a problem which I have here for a fractional case. So here is a coupled partial differential equation actually. So you have the team of problem I was solving with one of my hosts here. So solving this partial differential equation, so you can see it's in U and V. U is a function of x, y, t, V is a function of x, y, t, and you can see the expression for V, U is present. So, but what we did is to solve this first one, solve it first. When you solve it, then you now put the expression of the solution of V in the expression for V and now solve. So, in cylindrical coordinates, so this is one thing we do. Remember, your initial problem is in x, y, t. So, what we do is to transform into cylindrical coordinates using this substitution, x equal to this and y equal to this. So if you use this substitution, then your equation, which you have, the previous equation now transforms to this form, which you are having here. So I've written down here, if x is r cos theta, y is r sin theta, then this is actually equal to this. So if you maintain axial symmetry, the terms containing theta goes up. So you have just this other term remaining, this one. So, and this one, there is a standard expression for finite Hankel transform, which can actually use. So we are now solving the fractional form of this coupled differential equation, partial differential equation. So we applied so look at the fractional form of the previous equation in 3.40. So theta is our fractional derivative. So I'm going to apply Laplace transform of the capital derivative to both sides of equation 3.40 together with the initial condition which is given to me. So if I apply, then I'm going to have the expression given in 3.42. So if you take the Laplace transform of the capital derivative, remember, this is nothing but the Laplace transform of the capital derivative. If I take the Laplace transform of the capital derivative, I apply the Laplace transform to this, then I'm applying Laplace transform in t. So basically what will change will be my variable. So I will just move from RT to RS. So every other expression will be the same. So this will be there. Then again for the second term, this will be there. So if I apply the initial condition, the second expression, the initial condition time t is equal to 0, my v is 0. So this is what happens. So I put the 0 there. So that term goes up. That term goes up. So I have got this remaining. So I solve the first equation. We solve the first equation of 2.42. So if I apply the zeroth order finite Hankel transform, because there is a standard result for the zeroth order finite Hankel transform of this expression given in 2.42. So if I take the zeroth order finite Hankel transform and if I apply it to both sides of the equation, then I will just have this expression which I have here. It's the zeroth order finite Hankel transform. Apply transform to this, I get this. Apply transform to this, I get this. Apply transform to the whole of this, I get this. So again, I'll apply the boundary condition. Look at the boundary condition, U8C. So go back to the previous slide. So as you are solving this problem, having a well-defined boundary condition is very important. So look at my boundary condition, U8C is 0. So if I apply it, if I apply this U8C, which is 0, so this time will go away. So I'll just have 1, 2, 3, all these other terms remain. So I'll just collect like terms. Again, I will also write it in a very nice form. So this is something you can do at your leisure time. You have this form, even in 3.45. So again, you can see the Laplace function is coming to mind. S power theta minus 1, S power theta, and then you have this. So if I take the inverse Laplace transform, so you can see in most of the inverse Laplace transform I've been taking, the Laplace function keeps appearing. So you can see it here. So a very good knowledge of this Laplace function and its Laplace transform will help you so much in solving problems involving fractional differential equations. So you have, when you take the inverse zero order finite Hankel transform. So this one, the inverse is in series form. So this expression will just give you what you have here. So I finished solving for my U. So URT is this final form, all this expression given here. So now the second equation is actually this. So what I do, I just pick this expression, I now plug it in the second equation. So I now solve. So solving it, I arrive at the same process we are following, as I've explained. So solving it, then you have this final form. You can see how these transforms are being helpful. So basically today, my aim is that, at least this is the basic idea, let's focus on all these transforms, integral transforms, and how they can really help us solve these. I hope if we really have more time, maybe in the nearest future, we can now look at some non-linear problems, which will be arising as you are doing your modeling, as you are designing your problem. Then in that scenario, we're looking at also some numerical schemes, which you can be able to use. So for basic idea, I believe the presentation today, to a large extent, is fine for us. So the last slide is thank you for listening.
Thank you, Dr. Andrew Omame, for a very well delivered lecture. Before we conclude, we want to find out if from our participants, if we have any questions. So if you have questions, kindly indicate by raising up your hands. If you have questions based on modeling with fractional differential operators, basic ideas as delivered by Dr. Andrew Omame, please kindly raise up your hand. If you go to one of the icons in your Zoom, you will see the symbol where you can raise up your hand, the icon. and then you unmute yourself. Okay, I think I've seen one. That's okay, someone is clapping. Please, you can raise up your hands and also unmute yourself. We have just a few minutes so that we can round up. Our time is already past 10.
Can I ask a
If
question
you don't
now?
have question, we
Yes. So
yes,
somebody
you
has
can go ahead.
Okay.
Okay, go ahead.
Thank you, Dr. Andrew, for the very nice presentation.
Thank you.
Unfortunately, I missed very much part of the presentation. I only came back towards the end. But my question is, so you've presented nice problems, nice way of solving them. But how do you confirm that you've gotten the correct solution? So when you have the equation, you do your Laplace transform, your Fourier transform, and get all the results. So how do you confirm? How do you know that the result you get is the actual thing, is the correct answer to the problem?
Yes, thank you very much, Dr. Chidi, for your question. So one way you can be able to compare, right? One way you can you hear me?
I'm hearing you, yes.
Okay, fine. So one way you can be able to verify your solution. Number one, of course, your steps. You make sure your steps are fine, right? Then, if for instance, I can be able to recover, if I can be able to recover the integer form of that equation. If you have, for example, if I'm dealing between alpha between 0 and 1, then I have my expression for the integer case. Then you can be able to say, okay, if alpha is very close to 1, then my fractional differential equation should be able to be close to the integer scenario. So, but once the right mathematics is okay, once you are following the right mathematics, you are following your steps, the right steps from the beginning to the end, you should be able to know if the solution you have gotten is fine or not.
Okay, thank you.
Okay.
Yeah. So, but
Okay,
again,
thank you very much,
yeah,
Dr.
just to add,
Omagwe.
yeah,
Yeah,
another thing again,
Emeka
another thing,
Francis. And,
yeah.
Emeka Francis, go ahead.
Okay, thank you, Dr. Andrew, for
Yeah.
a well-articulated lecture. I
Thank you.
sincerely appreciate that. So I just want to ask a fundamental question on using the fractional order for modeling. So I want to ask, how do you justify, or how do you know actually the kind of, fractional order you use, that is going to use Capto, Fabrizio, ABC? How do you know actually the one to use when you are doing modeling? How do you justify the particular one you use? Thank you.
Yeah, this is always a question anytime you have a seminar or talk on fractional differential equations. So, but just like as I've already presented, for example, if I have a modeling problem that involves initial condition, maybe at time t is equal to 0, my total population is this, at time this is equal to 0, my total population is this. So, if I have a problem involving initial and boundary condition, the best form of fractional derivative I will use will be the capital fractional derivative. Because you can see from the definition of the Laplace transform for the capital fractional derivative, the initial condition is defined. So basically, you will ask yourself, what are the initial and boundary conditions that you will place on your problems? Then you check all the different definitions. Does this definition, can it be able to accommodate the initial conditions and boundary conditions I have? Will this fractional differential operator or equation be able to accommodate the initial and boundary condition which I have defined? For example, if I have a problem that tells me at time t is equal to 0, my u value is this. So I know the Riemann-Liouville, the definition of the Laplace transform for that in the solution. At time t is equal to 0, I don't have an expression in the solution that can be able to capture that. Then I will not use the Riemann-Liouville fractional derivative. Rather, I will use the capital fractional derivative. Same thing with the Atangana, same thing with the capital Fabrizio, and any other fractional derivative. So you just check the definition of the derivative. Check and see. And it be able to accommodate the conditions you are placing on your problem. If the conditions you are placing on your problem cannot be accommodated by that fractional differential operator derivative, then no need to use it.
Okay, that makes sense now. Thank you.
Thank you very much, Dr. Andrew, for all those well-articulated answers. We want to take just one more question, if we have any. and round up. Just one more question, if we have any. Any question?
I can see somebody.
Okay.
Yeah, somebody is chatting. The obtained solution is a solution if it has the required regularity. Yeah, this is another contribution to the last question, I think. So the opportunity, this is another addition. The obtained solution is a solution if it has the required singularity at somebody posted. So the opportunity is another.
Yeah.
The obtained solution is if it has the required singularity and has zero receiver. So this is a contribution I think from Sephira. So I think this is an addition to the answer to the opportunity. So you can take this also as an addition.
Okay. Okay. Thank you, Dr. Andrew, for the answers. And I want to appreciate everyone for joining us today in FUNOG. FUNOG is a Functional Analysis and Optimization Research Group, a research group based in the Department of Math Photo. And we have members across the nation and internationally. So we thank you, Dr. Andrew. Dr. Andrew is a member, a faculty member at the Department of Math Photo, and also is currently with the Abdul Salam School of Mathematical Science, Lahore, Pakistan, for his postdoctoral fellowship, and is a well-published author. And we want to appreciate him. And like we said at the beginning, this seminar is in honor of our former dean, the School of Physical Science in Futo, in the name of Professor CCZ Ako Lisa, who have actually laid a very solid foundation for us at the school here in Futo for research. So we appreciate his contribution, and we also appreciate the presentation of Dr. Andrew. Once we have another presenter, we are going to announce it to us. So I want to also appreciate every one of us. I appreciate every one of you for joining us. So from me here, we've come to the end of the seminar for today. So thank you everyone for participating. May God bless you all.
Thank you very much. Thank you. So I will share the slides in some moment. I will share it because
yes, I wish yes, send us the slides
yes,
so that we distribute to them. You send me the slide and then we will share it.
All right. Thank you very much. Thank you. So thank you everyone.
Thank you, Dr. Andrew. We agree. Yeah.